All right, good morning, everyone. It's 9 o'clock. We'll go ahead and get started. I see a few folks still coming in, but we'll get started. Appreciate everyone joining us this Thursday morning, February the 25th, 2021 for VC Ag Today. Our topic of discussion today is going to be agricultural drainage. And as many of you on the call probably know and have experienced, we've been pretty wet over the past several months here, especially in Eastern Virginia. A lot of flooded fields still with standing water. A lot of stuff needs to be done in the fields coming up to prepare for planting. So hoping to have a discussion today on how to address some of those issues. And we're pleased to be joined by Dr. Zach Easton in the Department of Biological Systems Engineering at Virginia Tech. So thank you so much, Dr. Easton, for joining us today. And he's going to share some of his input on agricultural drainage and share some information and background on that. We've also got some information that has been shared with us from the USDA Natural Resource Conservation Service on installing some of these drainage systems and some steps that you may need to go through for that. So we're going to provide some information on that as well. And I think we also have a grower on the line with us from locally here in New Kent County that maybe can provide a little bit of background and information on drain tile installation. So Mr. Paul Davis, thank you for joining us as well this morning to offer that perspective. So before we get started this morning, I'd just like to cover a few Zoom etiquette rules. If you would, please keep your microphones muted through the presentations this morning to avoid background noise. If you have questions or comments, if you could enter those into the chat window or just save those to the end of the presentation, we'll be glad to address those at the end. And hopefully have a good discussion this morning. So without further ado, Dr. Easton, thank you for joining us.
No problem. Thank you. Glad to be here. So I'm going to share my screen here. So it's going to take away your share if that's okay.
Yes, sir.
And so I guess before we get going, so I did put together the documents that the NRCS shared, as well as some other documents that would be helpful in discussing agricultural water management and drainage. These are the NRCS Engineering Field Book chapters that are relevant to drainage. So there's water table control and drainage water management, and then a few VCE publications that are relevant to this topic as well. And so I'll share all of these with Robbie and my presentation as well after the presentation today. And I guess there's this other form too. So sort of just an FYI on what you should do if you're thinking about a drainage system. Okay, so like Robbie said, we've been pretty wet, not only this year, but I believe that at least in some areas of Virginia, 3 of the last 5 years have been some of the wettest on record. So we're definitely having to deal with a lot of water in our fields, and having to try and get the water out of the fields is a big issue. And the way people do that traditionally is with drainage. So basically what I'm going to talk about today is agricultural drainage basics, both tile and surface drain systems, so subsurface and surface drain systems. We'll talk about why this might be relevant now, the various benefits of drainage, the different types of drainage, so surface, subsurface, etc., various system designs, regulations that you're going to want to be aware of before you consider drainage, and then some of the impacts and how we can mitigate those impacts of drainage. So why is drainage needed? Well, because our fields are too wet, these crop yields can suffer. So they can either decrease the yields, or we can have much more variable yields between or through years if we have poor drainage. We can also have limited access to the fields. I think like Robbie said, there's going to be some concern about getting to the fields come planting time this spring. And drainage can help with all of that. It can even out your yields, it can increase your yields, and it can increase access to your fields for operations. So the need for drainage is really driven by a high water table in the soil profile, or some sort of ponding on the soil surface caused by some low permeability soil layer or some sort of impermeable layer in the soil that restricts vertical movement of water. So you can't get it leaving the root zone. So why do we need drainage? So like I said, 3 of the last 5 years have been some of the wettest on record, and it looks like these trends are going to continue into the near to moderate future. So these are some predicted precipitation trends for the Mid-Atlantic using some of the global climate models that are out there. So this is the sort of short term, so 2040, 20 years from now, what might our precipitation regimes look like? And what you can see from the projections, and these have largely been borne out by recent precipitation trends, is we're seeing some pretty dramatic increases in winter. Well, I call it winter. Oh, sorry. I got a new mouse that I've got to get used to here. So we've seen some pretty dramatic increases in precipitation, particularly in the winter and spring, so non-growing season. And those trends look to continue. So there are areas of Virginia where I am right now, Blacksburg, they're projecting, a 15 to almost 20% increase in winter precipitation volumes. And all of Virginia is projected to see a pretty significant increase in those precipitation volumes. Eastern Virginia, the Delmarva is less, but still, 5 to 10% increase in precipitation can be pretty significant. And Virginia is a little bit different than the rest of the Mid-Atlantic in terms of summer precipitation changes that might be expected. So what you can see from the figure on the left is that a lot of areas of the Mid-Atlantic are expected to see a decrease in summer precipitation, indicated by the red in that figure. Well, Virginia is projected to see an increase on the coastal plain in Delmarva and pretty much no change elsewhere. So overall, what we can expect is an increase in the total volume of precipitation, which means we're going to have wetter soils that we're going to have to deal with in our operations. So here's another image that I thought was relevant. So this is a map of the percent of the conterminous US that meets a criteria of having some sort of impermeable layer in the soil. So most of the soils on the East Coast have some sort of impermeable layer at some depth in that soil. So this impermeable layer can be like a fragipan caused by glaciation up in the northern reaches of the US. So New England, Pennsylvania, that's all glaciated. So you can see much of the landscape has restricted drainage. In our area of Virginia, we're a little bit different. We have karst features on the western edge of the state, which does have some features that restrict water movement. But on the coastal plain and the Piedmont, you can see that there's also a significant amount of area that has some sort of feature in the soil that prevents drainage. And so this is another reason, this coupled with the increase in precipitation is another reason that we're probably seeing increasing interest in drainage being installed in our area. And that's a large reason why. And then I just zoomed in here. I probably should have done that to start. It's kind of grainy, but you can see again, so over here on the coastal plain, up to 30% of that area meets that criteria of having some layer that restricts vertical movement. And in fact, this analysis was pretty strict. So they only looked at physical soil features, but in fact, there's other features that can restrict drainage in the soil. So in fact, I would estimate that probably greater than 50% of the soils in Virginia have some sort of layer that restricts drainage. Okay, so what are the benefits of drainage? And I think most people probably understand this one pretty well, right? So more consistent and or increased yields. So if you look at the history of drainage out in the Midwest, the yield increases were pretty staggering with the addition of drainage. In our region, however, the yield increases tend to be not quite as staggering, but what you see in our area is much more consistent yields from year to year. This shows what the increases might be. And again, this is out in the Midwest. I believe this is in Iowa. So, up to almost a 40% increase in corn, 41% increase in wheat. Again, these are big increases in yield, which probably aren't typical of what we'd see with the addition of drainage here. We'd see probably less variability. Another thing that people probably don't think about quite as often in terms of one of the benefits of drainage is better access and timeliness of field operations, right? You don't want to end up with a situation like this in your field. That's a pretty expensive mess right there. The drainage could probably help you avoid. And so with proper drainage, you can get earlier and more timely planting, improved harvest conditions, and less wear and tear on your equipment. So wet soil causes you require more power to motivate through it, and it causes more wear and tear on the equipment. So drainage has benefits with respect to that as well. And then finally, something that's more recently come on the radar in terms of drainage is trying to deal with drainage discharge. And we'll talk about this at the end of the talk today. So drainage does present some challenges for environmental quality. So water quality, hydro modifications, those are all things that you need to consider when you think about a drainage system. But there are opportunities to control and treat those discharges. In fact, use those discharges, the drain discharges, to your advantage in some cases. Okay, let's go into sort of ag drainage basics, right? And so what I think I want people to recognize is that there are different practices for different conditions. Traditionally, I think most people think of, when they hear the term drainage, they think of the traditional tile drain, a pipe in the soil that's draining a field. But in fact, there's lots of different types of drainage. And depending on your operation, tile might not be the best solution to a drainage problem. And so this just shows some images of the different types. There's surface smoothing, there's ditching, there's subsurface, there's grade control. We'll look at all of these briefly as well. But the goal of any drainage system is to remove excess water within 28 to 48 hours after a saturating event. So some of the different approaches, like I said before, there's a couple different approaches to dealing with poor drainage. And it really depends on what your problem is or the characteristic you're trying to deal with for drainage. So if you have low infiltration rate, so heavy clay soils, compacted soils, things like that, subsurface drain might not be the best solution. In fact, I'd argue it's probably not the best solution because you have such limited movement of water in those, low infiltration rate, highly compacted soils, that water isn't going to move into your drain line with any sort of speed. You're not going to drain that field within the 24 to 48 hour sort of recommended time frame. So one option there is surface smoothing, so grading your land so that it drains following surface topography. And that's one solution. Now, if your soils are completely saturated, so they're poorly drained, you have a high water table, something like that, but they're not compacted or clay soils, so you have good potential infiltration capacity, you just have saturated systems. In those cases, a ditch or a tile may be appropriate. And again, it depends largely on your specific situation. So again, I guess I would reiterate that the drainage is not a one size fits all solution. A drainage system needs to be designed specifically to your problem and your system to have it function properly. You can also have soil with those shallow impeding layers, which I mentioned previously, right? Something that restricts vertical drainage through that soil. And in that case, ditches or tiles with surface inlets may be appropriate. So if your shallow layer is really close to the soil surface, maybe it's something that's a tillage caused layer, so an argillic horizon in the soil caused by 200 years of tillage. Then what will often be done is they'll put the drainage layer, the drainage line below that layer, and then put risers or surface inlets to get above that layer and drain that layer down. So there's lots of different options for system design, but really you need to understand what your problem is and what your field or production system looks like. Okay, so let's talk a little bit about surface drainage. So surface drainage, there's two really different types of surface drainage. One is land leveling and one is ditching. And in fact, they're often used in combination. And so surface drainage is good for water originating on site. So you don't have water from some neighboring property flowing onto your property, right? It's something that's originating from on your site, rain falling there perhaps is the best thing. Again, like I said previously, it's also most applicable for fine clay textured soils with low permeability and for areas with surface depressions. So, I mean, I would argue that land leveling and ditching is applicable to a lot of Virginia. The Delmarva is extensively ditched, and it seems to work pretty well in a lot of the situations there. So don't sell it short, I guess is what I would say. It can also be quite a bit cheaper than installing subsurface tile. some things to consider if you're going to consider smoothing and or leveling, right? So it's mainly meant to remove small irregularities. So something, cut and fill less than 6 inches. If you're trying to level a field where there's greater than 6 inches in sort of micro topography, you're going to have to account for soil settling following the smoothing and for topsoil removal. You want to be really careful with that topsoil, right? If you're scraping your fields, you need to consider what you're doing with that topsoil and where it's going. The nice thing about surface smoothing alone is that it requires fewer surface ditches to drain that runoff from that profile, from that field. If you can get a nice grade to your ditch, you can have fewer grades across that field, which increases the tillable acreage or the farmable acreage. And you can also have more efficient equipment operation. So a level field is obviously easier to run equipment. And it can be done for the most part, well, in some situations with some pretty simple equipment, right? You can just do rough grading with your tractor and scraper to fix, small irregularities. You can rent land planes or levelers. Those have a much smaller or tighter tolerance. So you can get down to less than a tenth of a foot tolerances. Or you can do precision landforming with level. These are custom operators. I don't know of any in this region, but there might very well be people that do these types of things. I think most of the surface smoothing in our region is done sort of at the farm level. So rough grading with a tractor and scraper for the most part. Okay, so what about surface ditches? So surface ditches, like I said, are another option if you have drainage problems associated with low infiltration rate soils. You'd couple it with the smoothing or with high water tables, right? So a ditch installed properly is going to dewater that soil profile. It'll remove the water, it'll reduce the water table in that soil profile, depending on the depth of the ditch. So again, you want to consider the source of the water if you're looking at a ditch system. So ditches are applicable to both on-site and off-site water that's originated from there. The topography is probably the most critical for a ditch. You need to figure out if you're going to do a uniform or an irregular spaced ditch system. So this one here is showing an irregular spaced ditch system. So they're just trying to drain specific spots that are wet. So these are, potholes or depressions in the landscape, and these can be drained pretty easily with a ditch. And you can use ditches on flat or sloped land. Things you want to think about with ditches are the soil permeability. Again, I mentioned this previously. So if you have really, really low permeability, it's hard for water to enter the ditch, right? There's not enough conductivity in the soil for it to move. And then field operations. Obviously, if you have ditches in your field, that's going to dictate how you can operate machinery on that field. This just shows more of a uniform type of ditch system. So you always want to run your cross slope ditches parallel to the topography. So you want the water flowing down the hill like this, and you want the ditch to intercept that water. So these are called interceptor ditches, and they're going to intercept that water flowing downhill, convey them to this outlet drain, which usually runs with the slope. Okay, so how do you determine what your ditch design might look like? There's a few things you're going to want to consider in terms of the actual ditch, right? One is the gradient of the ditch, so the slope of the ditch, the bottom slope of the ditch, which dictates basically the velocity of the water in that system. So if the water flowing in your ditch is too slow, so your slope is too shallow, then you're going to get sedimentation, right? You're going to get your ditch filling up with sediment. And if it's too fast, you're going to erode that ditch and get scour. So those are both things you're going to want to consider. You also want to consider what's the steepest side slope you can have to avoid failure, but also be able to maintain it. The ditch bottom grade is, like I said, basically what determines the velocity for any of these given shapes, right? So these are all the different shapes that a ditch can be. And in fact, there's more than that. But at the end of the presentation, I'll go and show you in the drainage guide how you might use this in your drainage design. And then, so I also say that it's limited by existing structures. And what I mean there is that if you don't have enough slope in your system to maintain the ideal velocity or the grade that you've determined you need, then you're going to have to figure out how to convey that water. So some of that involves pumping, which can get expensive. So there are things you can do there if you don't have the slope, but you're going to want to consider the slope of that system. And then finally, the capacity of that ditch is simply the velocity of the water in that ditch times the cross-sectional area. And so that gives you the flow, the design flow volume that you need to figure out your drainage. And so the velocity and the area are basically functions of that ditch shape. So each of these different shapes is going to have a different, well, obviously area of the ditch and a velocity of those ditch. And those are all in those NRCS drainage guides. Again, so like I said, the goal is to remove runoff within 24 hours following a rain event. And so here is the equation that's generally used to estimate the amount of flow that a ditch would have to convey to meet your drainage requirement. And so what they use is what's called a drainage curve number. And I've put in a couple here. Again, this is from that drainage guide specific to Virginia. So most of Virginia falls in the northern humid climate, and then you'd have a drainage curve specific to pastures and one to, say, cultivated grain crops. And then, the eastern shore of the Delmarva has a little bit different drainage curve numbers. And so depending on where you are in the state and what land use or crop type you're using, you'd select a drainage curve number. So let's do an example here. So let's say we're on the Delmarva and we've got a pasture on the Delmarva. So our drainage curve number would be 30. And we're going to ditch drain an area of 0.2 square miles. So if we plug those two in our equation, we see that this ditch, this theoretical ditch that we're planning to install, would need to be able to convey 8 cubic feet per second of water out of that 0.2 of a square mile drainage footprint. And so ditch design is pretty straightforward. There's not too much that's complicated about it. Again, I guess I would reiterate that slope is pretty important in ditch systems because you want to maintain the proper velocity of that water. Okay, so what about subsurface? Again, I think this is probably the more common drainage situation that people think about when they start thinking about agricultural drainage. And all subsurface drainages is drain pipes, or tiles they're often called, because historically they were actually clay tiles, about a foot long, that were placed in the soil. Now they're all, well, not all, but they're mostly ADS plastic and things like that, placed at some depth in the soil profile to dewater or remove all the water above saturation in that soil profile. And so I think what might be a common misconception about drainage or subsurface drainage is that it removes all water from the root zone. And that's not true. So the only thing that subsurface drainage does is removes free water from the root zone, right? So it's removing the water above field capacity. So the saturated water content of that soil. It's not removing water that's available to the plants. So everything that a plant would normally have access to, it would still have access to in the presence of drainage. And I think that's an important point to be made. So subsurface drainage reduces a lot of different problems associated with water stress, right? So waterlogged soils basically prevent roots from taking up oxygen, which can cause the buildup of toxic gases in that soil, which inhibits the root development. And we really want to prevent this, especially at germination. And so our goal is to prevent the sustained saturation, but not remove all that plant available water. And you can see that's what we're showing here. So if we have undrained land, you have a very high water table in the spring, which dramatically restricts that basically root development and root penetration into that saturated soil. And as a result, you get sort of stunted growth throughout the season, even after that water table has receded. And this has been pretty well documented throughout the US. On the drain land, again, in the spring, you're going to draw that water table down so you get more full root development and root penetration into that soil profile. It can access more of the nutrients, more of the water, the plant available water in that soil profile. And again, this reduces problems with disease, variable yields. Soil temps is another big one. People don't think about that very much either, but a drained soil dry or heats up faster than a wet soil. So even if you could get into the wet soil and plant, you're going to see reduced germination due to lower soil temps because of the soil is wet. You can also, and maybe I shouldn't say reduce problems with runoff and erosion, but a properly installed drainage system can help with problems with runoff and erosion. I'll talk about that a little bit in a few more minutes. Okay, so what about some of the layout and orientation of subsurface systems? Again, they're pretty flexible, just like ditch systems are. You can have them drain random areas of poor drainage. So again, maybe potholes or depressions that you want to drain. You can do parallel grids, herringbone. Again, there's lots of different designs that you could consider. The one thing I would caution you with is that you always want to align your laterals, right? So these laterals here with the field contours. So you don't want to have them crossing those field contours. Otherwise, it's never going to drain that land. One other thing to point out, right? So these laterals, we call these, right? These are usually relatively small drain tiles. So these are generally 3, 4, or 5-inch perforated pipe. And it doesn't really matter what the size is here. Larger pipes have more openings for water to enter in, but your drainage system isn't constrained by your design size of your laterals. Your drainage system is constrained by the design size of this main. So we'll go in and see how that, see how we can determine that, at least roughly figure out what our design main size is, because like I said, again, that largely dictates the system conveyance. Okay, so some things to consider in subsurface drain design, different factors for depth and spacing, right? One is the soil permeability. Again, we mentioned this previously. Heavy clay soils or compacted soils probably not amenable to a subsurface drain design. More permeable soils, however, are. Soil depth, again, the depth to some layer that restricts drainage, you need to know. Obviously, the crop type you're planting is important, right? Is it a field crop or a truck crop, or sorry, a row crop? Again, this goes back to that layer in the soil. Is there something that restricts drainage? And then different climates that you're trying to deal with, and grades and topography. And this is all important because you want to have, oops, sorry. You want to have your drains correctly spaced, and all these factors, and I'll show you in a minute how we calculate this, all these factors largely determine how our drainage system functions. So you want your drains spaced a specific distance apart as a function of the different factors of your system. And so with a correctly spaced, and these are laterals here, again, these are the ones that go out into the field, you're going to be able to draw that water table down within 28 to 48 hours, so you don't get restricted plant development in this areas. If drains are spaced too far apart, well, then you're going to end up getting a high water table in this area of the field, which is going to impact your yields essentially. And then I guess I'll show this on the side. So this is the effective depth to that restricting layer on drainage spacing. So if you have a drainage system installed with fields with a shallow restricting layer, as in the image on the right, the drains in that soil need to be spaced more closely together and or closer to the soil surface than in a system in fields with a deep restricting layer. And this is really because that shallow layer that water can't move through essentially prevents soil water from reaching that tile, via flow paths that are deeper in the soil. And so what this actually does is increase the cost of system installation, because now you have to put in more drains, and it reduces the system effectiveness because those drains are now closer to the soil surface, which essentially means that your water table is closer to the soil surface, hence possibly causing saturated soil and reduced plant growth. So again, this comes down to understanding the system you're working in. If you're in a system where you have a gillic layer at 10 inches, that's something you're gonna need to know about when you go to design your system. Okay, I said that the size of the lateral isn't very important, and it's the size of the main that's important, but the spacing and depth of those laterals are very important. This is the critical sort of step in determining the lateral design of your system. And so there's a whole bunch of equations that have been developed to predict or to space these drains, right? To figure out the spacing of the drains and actually figure out what that water table height will be with a given spacing and a given depth in the soil. This is a derivative of one called the Hooghout equation, which is out of the Netherlands, which are extensively drained. I think something like, almost 80% of the Netherlands has some form of subsurface drainage in it. So they're experts in drainage. And so we use this equation to basically figure out how far apart these drains should be spaced in the soil to achieve a given drawdown. And so S is that drain spacing in feet. And there's three things we need to figure out in this equation. One is the hydraulic conductivity. And so the hydraulic conductivity is the speed at which water can move through a given soil profile. So you can imagine sands have a higher hydraulic conductivity than clays. They can move water through them faster. So in a drain design, that means that water can move out of that soil profile into a drain more quickly. And then another one is the drainage coefficient. So this is the design rate at which water is removed from the soil profile. And this is specific to the soil and the crop. And there's tables for this that I'll show in a minute. And then B, which is the distance from that water table to that restricting layer or barrier in your soil. And again, if there's no barrier, then there's just an assumption about what that depth should be. So some things that you're gonna need to consider when you're thinking about your spacing is a soil type and how much capillary rise you might want to build in this, right? So this may be the boundary that defines, the saturated, system down here, and then the unsaturated soil up here. But in fact, there's going to be a gradient in moisture due to capillary rise. So the soil pulling water up into the drier soil. So you could determine how high you want that rise to go, which can help, with crop growth. And then the crop requirements in the root zone required for that crop. Some crops require a deeper unsaturated zone. So you can include that in your calculations. The type of equipment that you're using, the tillage, are you dealing with frost in the system? Not such a huge concern around here, but I guess if we look at Texas last week, it could be a problem. So maybe something to consider. Layer permeability and then outlet location. Those are all things that you're going to need to think about in your drain design. So I mentioned that there were sort of three things we had to know about. One was the drainage coefficient, right? V, and that's in inches of waters per day. And like I said, the drainage coefficient is basically the design capacity that we need the drainage system to deal with. And it's always expressed as sort of a depth of water removed in 24 hours. And again, these are from the drainage guide. So you can go look these up. And I sort of generalized here. So you have two soil types, organic soils or mineral soils. Most of ours would be classified as mineral. And then you have field crops or row crops. And so in some of these, you might argue that one or the other of these is a better value to choose from. And you do that basically using expert knowledge. So if you know something about your soil permeability and your crops and your climate, then you can pick a more representative value. And in fact, what I usually do when I'm thinking about drainage design is I'll plug in both ends of the range just to see what my potential outcome could be. So I'll plug in, if I'm doing a row crop on mineral soils, I'll plug in a drainage coefficient of 1/2 and I'll plug in 1 3/4 and look at both answers. So we also need something about the soil hydraulic conductivity. So historically, this was often either measured on site through some sort of borehole test or drawdown test or pumping test, although those can be pretty expensive to conduct. But more recently, the USDA has produced what's called the Web Soil Survey, which I'm showing a screenshot of here, that you can go in and basically map out all the soil hydraulic conductivities for your area of interest. And so you can get a map, and then it produces the values, in this case of the hydraulic conductivity, which you can use in your equation. And so that lets us estimate the spacing and depth of the drain, again, of those laterals, which is the first step. But again, I said that it's the size of the main, right? That's the most important one. And so this is the equation that's used to calculate the flow that our main line, our main drain line, is going to have to deal with. And that's the pipe hydraulic capacity. And it's a pretty simple equation, much simpler than that other Dutch mess we looked at. So all it says is that the flow that a tile main is going to have to deal with is the area that's being drained times that drainage coefficient divided by 23.8, which is just an empirical conversion. So let's do an example. What flow capacity is needed to drain 60 acres with a 3/4 inch day drainage coefficient? Well, so if we plug those in to our equation to figure out the main sizing, we come up with an estimated flow of essentially 1.9 cubic feet per second. So that's the amount of flow that main line is going to have to convey for our drainage system. And then what you do with your design flow, you go in to the NRCS drainage guide, or there's commercial drainage guides as well. I like the NRCS one personally, and select your size. And it's going to depend on the pipe and the material and the grade. And I've got an example of that here. So again, this is from the drainage guide, and I'll show you the example we did here, but all we're showing here is this is the design flow rate side of the table, right? So it's got the drainage coefficient and then the acres that we're planning to drain. And then over here, it gives us the pipe size and the velocity of the flow in that pipe. It also gives us the discharge we can expect. So let's do our example here real quick just to see. So we have a 3/4 inch drainage coefficient. Let's assume a 1% slope and 60 acres, right? And I guess I should also note that 1% slope, I'm sorry, is the slope of the drain, right? It's not necessarily the slope of the land. It could be, if your land has a perfect 1 degree slope, you can set your drainage plow, to 1% and it'll pull it perfectly. However, in a lot of systems, particularly very flat systems, low gradient systems, you're going to introduce the slope with your drainage plow. So something to consider. So slope is a function of the equipment as well as the field you're working in. So if we take our 3/4 inch drainage coefficient and we go up to 60 acres, and then across, we come up with our, and I'm going to zoom in here a little bit, maybe I'll make it a little bit easier to see. All right, 3/4 inch drainage coefficient that's draining 60 acres on a 1% slope tells us that we need a pipe, a main size of about 12 inches, right? And it's almost perfectly in the middle of that 12-inch pipe size. We're not up near a boundary where we'd have to flip up to a 14-inch pipe or something like that. So this would say that a 12-inch pipe is suitable to drain the 60 acres at a 1% slope, 3/4 inch day drainage coefficient. You can also use this table to figure out what your design flow is. We did that with our equation, but if you knew the acres and the drainage coefficient and the slope, you wouldn't need the equation. You could basically just figure it out from this table. Okay, so what are some of the limitations of subsurface tile drainage? Well, one is a lack of outlet, right? So if you don't have enough grade in your system to what they call daylight that tile main and do either a ditch or irrigation pond or something, then you're probably going to have to pump that system, which again gets pretty expensive. Lack of slope can also be a limitation. Like I said previously, slope can be to some extent determined by the drainage plow, but in essentially zero slope systems, in large fields, that can be a challenge to deal with. Low permeable soils, again, we talked about that. That can be challenging with with tiles. Obstructions, so do you have to go around or through things in your fields to get the water out of there? Subsistence and sandy soils, I added this because a lot of the Delmarva and coastal plain has sandy soils, so you can see subsistence following subsurface drain installation. And then economic return. Now, I'm not an economist, but there are some pretty nice tools out there to estimate the economic return. And again, the economic return is highly site specific, right? It depends on the value of your crop, the yield increase as a result of drainage, the complexity of the site. So there's a lot of things to consider there. Now, I kind of went through some examples using sort of the classic drainage equations because I guess I like to think about it like that. But there's also some very nice calculators out there that you can use to either figure out, say, your drain spacing. So this is one that I like, South Dakota University Extension, a lot of drainage up there. But you can use this, again, you put in your drainage coefficient, the typical tile diameter, this is for laterals, depth, etc. And it'll tell you what your drain spacing should be. So pretty nice little system. I guess I'll talk about economics really quickly. Like I said, I'm not in economics. And again, there are some pretty nice tools out there to do this. And I used one of these tools to kind of come up with this little example. So I said we had 50 acres of tile drainage going in on 75-foot spacing. And I assumed about $900 an acre was the cost. Now, we have someone, I believe this morning, who might be able to update that for us. But for this example, let's assume that total 50 acres costs $45,000. But let's say on this 50-acre field, half of it was poorly drained and half of it was pretty well drained. So you're probably going to see a much bigger yield improvement on that poorly drained soil once you drain it than you are on that moderately drained soil. But for this example, let's assume we drain all of it. And these are what, let's say the price of corn in bushels, the equivalent in silage, and then the yield improvement. So either the yield in corn or the yield in silage improvement, and then the increased revenue from that yield. I guess one thing that people probably don't consider is that there's increased production costs associated with those increased yield, which you're going to want to consider, right? So you're probably going to have to apply more fertilizer. There might be more harvest and storage costs. So those are things you want to consider in drainage economics. But again, you can see that in this case, there's about a $125 per acre increase in net income, which is pretty significant. And so if we average this out over our total cost, we get about 7.2 years for payback with these two assumptions: 10.2% internal rate of return, which obviously right now, well, that's what this calculator assumed. I don't know if that's a good assumption or not. I should probably talk to an economist to see. But some nice things that these types of tools allow you to do is they can, you can ask the question, well, how much do I want to do at once, right? You want to do the worst drainage area first, obviously, but do you want to do all of it? Does it make more economic sense to only do a fraction of it? And then how much does drainage cost compared to other strategies, right? So is it cheaper to go out and buy or rent other land or to buy more feed and bring it in? Those are questions that these can help you answer. Okay, so last couple of minutes here, I wanted to get into some of the regulatory issues and then some of the environmental consequences of drainage. So there are several different laws or regulations that govern drainage or hydro modifications, right? So USDA, NRCS, the farm program, they can withhold benefits from anyone who essentially drains a wetland after 1985 or converts a wetland after 1990 for production, essentially. So those are two pretty clear regulations that most producers are probably aware of. So a couple other ones that people, and these are the ones that can get people in trouble, and these are the ones that I've seen get people in trouble. And those relate to EPA and US Army Corps of Engineer wetland regulations. So the discharge of dredge or fill material, including wetlands. And so most routine farming activities are exempt, except when you're dealing with wet areas. And I say wet areas, not wetlands, because most of the wet areas, well, maybe not most, But it turns out that a good deal of the wet areas that we may see could arguably be classified as ephemeral wetlands. And so you need to be careful about wet areas in general. You also need to be careful about hydromodification, right? Hydromodification is where you've changed the hydrologic regime in that system. And what this does, so drainage, right, it reduces the water table in that system, so dewaters that soil. And this can influence, say, the contribution of soil water to wetlands, so groundwater flow into wetlands. So there are rules to be aware of with respect to hydromodifications. So always be in touch with USDA before draining or doing anything in wet areas. Always just a good idea. And then what are some of the environmental consequences of drainage? Well, one is water quantity, right? So these figures are showing drainage density on the x-axis. So that's just, how many drain lines do we have, or tile lines do we have, or ditches do we have in a given field? And then the water residence time. So this is how long the water spends in that field. So you can see that the more drainage we put in, the less and less time water spends in that field. And this means that soil water has less contact with the soil, which usually, the soil is pretty good at holding on to nutrients if it can. If it doesn't have enough time for those chemical reactions to take place, well, then they get exported with that drainage water, which can be a problem. So increased drainage density can also increase base flow, right? So you're reducing surface runoff, but you're basically increasing the speed at which water is exported from that field. So again, these are two examples of the hydromodification rule and things you're going to want to think about in the system. There's also there's also water quality consequences of drainage, and they can be both sediment. They can be sediment, so you get increased erosion at tile outlets if they're placed improperly. Nitrogen is probably the biggest problem with tile systems. So, drainage aerates the soil, which increases nitrification. So it's good for plants. But nitrogen use is essentially inefficient in plants, right? It's leaky. So we get increased export because of drainage, increased nitrification. And there's been some recent work on increased phosphorus transport in tile drain system because of macro pore flow. So I'm not sure if you can see it in this picture to the right, but there's big worm channels here that allow this dye to flow right down, 10 feet into the soil very quickly. So the same thing happens in tile systems. Phosphorus can move from the soil surface deep into that profile. But there are things you can do to mitigate some of these impacts, right? So in ditch systems, what people often do is they dip out, they call it dip out the ditch. They scrape it to remove excess vegetation and sediment nutrients that are trapped into that system. But what that does is it mobilizes a lot of sediment. When you scrape a ditch, you're removing vegetation and opening up the soil for erosion. You can do some interesting ditch designs as well. So two-stage ditches or ditch meanders and things like that. Flow control structures to reduce the speed that water is being conveyed through these systems. And then there's things you can do with reactive barriers or filters to remove nutrients and things like that. And in tile systems, you can do some of the similar things. You can do water table control, and actually you can do some irrigation in tile systems as well. You can do barriers and biofilters, or you can connect them to wetlands. So there's a lot of work being done on connecting tile outlets to wetlands. Again, just some pictures of what these might look like. So here's a ditch being dipped out. They're scraping all the sediment and vegetation out of this ditch to try and improve conveyance, so the speed at which water's moved through it. Here's a ditch that they're allowing some meander in, right? So the water can sort of interact with all that vegetation, and it slows it down as it meanders, so it reduces the energy, less erosion. Here's an example of a flow control structure. You can close that flow control structure, back water up in the ditch, which can do a couple things. It can improve water quality, and you can also use it for some basically sub-irrigation in some cases. So for subsurface systems, I think this is a really interesting opportunity for subsurface drainage system. That's water table management. And there is a conservation practice standard for water table management. In the presentation, there's a link to it, so you can get to it if you want. But basically, it allows you more efficient use of rainfall and decreased need for irrigation. So what you're doing is basically adjusting the water table height to some level that you've determined you want that water table at. Maybe it's to provide moisture to, you know, a growing crop. And this is what that might look like. So you've got your subsurface drainage system. You can either have it running in full drainage mode. So everything's being drained, you know, above field capacity. You can do controlled drainage where you've now sort of adjusted that water table to a specific height by putting in weirs, say here, or you can do sub-irrigation where you're now pumping water back through your drainage system into your root zone. And then this is another BMP for subsurface drainage. This is essentially a bioreactor. So it's a big, essentially excavation at the outlet of a field that's filled with organic carbon, which removes nitrogen from the field. You could also have a wetland here doing essentially the same thing. Okay, so wrapping up on this last slide here, I've got a bunch of different resources that might be helpful. Again, so the National Engineering Handbook is a great resource, I think, for all things agricultural engineering related. But there's two chapters that are particularly relevant to drainage. One is water table control, and one is the drainage water management. And so I will share those as well. And then a couple of publications, two that I put together on drainage and soil water basics, and then one from the University of Minnesota. They've got a really good drainage guide, a lot of drainage up there. So they've got a lot of resources that are helpful to us. And then local drainage contractors are always good sources of information. And so I think I might have gone a little long, but if there's questions or comments.
All right. Thank you, Zach. Appreciate the presentation. A lot of information, and hopefully it was helpful for some folks to get them those resources and share some of the understanding of these drainage systems and the different options that are available. I don't see any questions in the chat, but before we move to two questions, I know we do have Paul on the line with us this morning. So Paul, do you want to comment briefly? I know Mike said you had some recently installed drain tile that you had put in. So do you want to comment briefly on that process and maybe some of the costs associated with it, just as a ballpark figure and that type of thing?
Yes, I'd be happy to. I noticed after listening to an irrigation seminar one time, I decided I wasn't smart enough to irrigate. And now I know I'm not smart enough to put in tile drainage either. But we are trying to do some of this. Can you hear me?
Yeah.
Okay. We had, I guess 3 years ago, we looked at investing in some. We don't have whole fields that need draining. We've got, you know, an acre here and an acre there, and they're not at a corner where you can just leave them out. They're out in the middle of the field, and we're paying $75 to $80 an acre rent on that flooded out land. So we were looking at a way to try to make that, and it's on rented land as well, to useful. It was going to cost about $5 a foot to get it installed. We're looking at 6-inch socked tubing. So we're doing it for about $1.50 a foot. We've borrowed a ditch witch, put 10-inch wide diggers on it, and we're getting about 1.5 to 2-inch slope per 100 foot, and it seems to be working real well. We've got some runs that are 1,000 foot long and some that are only, say, 400 or 500 feet long. We're just beginners. Last year we put in 2,000 feet. This year so far we've been able to get in about 3,500 feet. And we've got another 1,500 feet we want to get done. But as you know, you can't dig in the mud and expect them to work. So we You do have to have somebody there that knows how to read a level. We've got a laser level that beeps at you if you're in the right place, and it beeps a lot if you're not at the right level. So you have to have somebody that's in the ditch that's able to read that piece of equipment. We've been satisfied with what we've done. We'd like to say to get the water out in 24 hours, but it's closer to 48 hours. But that's better than letting it sit there for a week or so.
Right. Yeah.
So anytime you want to come down and look at what we've done, and you're welcome to come down, Doctor.
Yeah, that'd be great. Yeah. I mean, yeah, and I guess I would reiterate, right, that what you just said, right? Each system design is custom. There's no one size fits all for draining. And that's what makes it more complicated than people think.
It's complicated. This one hole that we were out in the middle of the field, and we haven't rented the land for 8 years, and this is 2 acres out there. We haven't gotten an acre, a bushel of anything off of. The shortest distance to drain it, I was going to have to go uphill 15 inches.
Mm-hmm. Yeah.
And I said, well, that ain't gonna work. By the time I get to the edge of the field, I gotta be, I'll be up to my chin.
Yep.
In soil. So we went the other way, went a little bit further, but it only had to go up to my chest to keep that slope.
Yep.
But it seems to be working, and I think it's going to be a good investment in the long run. I do have a question. The life expectancy, we've got most of our fine sandy loam soil, and it has the socks on it. What is the life expectancy for this thing to work if it's 20 to 24 inches underground?
Well, I mean, that's a good question. I mean, I've seen drain tiles that were installed in the late 1800s still functioning, right? So sedimentation is probably the biggest issue, but you have socks on yours, so that's not going to be a huge issue. I mean, and I'm assuming you're using ADS drain line, or is that the case?
It's 6 inch.
Yeah. So if you get too deep, right, if you're talking about a 6, you said you were up to your chin, right? So anything over
only
5 or 6 feet, you're going to start to have to think about, compression of the tile, being crushed. But I mean, I think you can depreciate your tile over like 16 years. So I think that's sort of the minimum they assume.
Thank you. Those only comments I have. I'm a beginner in this. I don't know all the science behind it. I just know water's got to flow downhill, and that's what we try to keep happening.
Yep, exactly.
Now,
Paul,
we don't do the wishbones or parallel. It's just these are smaller areas, so we just have go right through the middle of it and try to drain it. I'm
Right.
sorry, go ahead, Mike.
Paul, you've seen really good results from draining your low areas as a result of putting tile in?
Yes, I see water in areas that we haven't done it. I've got water still standing in the field where we did put this in. In worse areas, the water has been already out of the field for 2 days, 3 days. So, and you can see water running out of the end of the pipe continuously, where these other areas in the field where water is just still standing there, and geese are swimming around in it.
So it is
Wildlife
working really
habitat.
well.
It seems to be working really well. We're satisfied enough to keep investing in it, even on rented land.
Good deal. Thank you.
Bobby, I had a comment about some of the old timer items. I was working with the superintendent or the manager of the Brandon Plantation, which is along the James River. And he asked me while I was down there one time to take a look at his field. And it was obviously a place within a field that it was a lot wetter. And he says, I've never had any kind of drainage problem in this field for probably 15, 20 years, as long as I've managed this place. And they started digging it up. And what they found was 3 cypress logs twined together.
Yeah.
And that was acting as a drainage
French drain, right?
yeah, in that area. So I just thought that was interesting that, you take the oldest continuous farm area down along the James River there, and they have some pretty old techniques for drainage.
Well, that's where I found that tile from the 1890s, was down right along the James at Shirley Plantation.
All right. Any other questions this morning for Dr. Easton or Paul, Dr. Grisso, and anybody on the call? Any other questions or comments this morning before we finish up?
This one. Thank you for having this such a timely program. And I do hope those graphs are right, that we are going to continue getting some rain over here.
Well, so far they seem to be the right direction anyways.
All right. Well, thank you everyone for joining us this morning. Hopefully this has been a beneficial presentation, and we can take this back to producers and share it with folks here in Eastern Virginia to help with these drainage issues as we continue to have this excess precipitation. Thank you, Dr. Easton. Appreciate you being with us and sharing all these resources. I will get with him and get those. So if you want a copy of some of those links and resources, just let myself or some of the other agents on the call know. We'd be glad to get you that information. And also, we have recorded the presentation this morning. So if you have producers or folks that you work with that may be interested in this information, let us know, and we can share that with them through the recording. So thank you all again for being here. Thank you, Dr. Easton. A few comments I'll make before we finish up. As always, I'd just like to thank my colleagues, the agents that helped make this effort possible: Stephanie Romelchek, Mike Broadus, Trent Jones, and Laura Maxine. Thank them for all their work that they do. And then next session that we will have VC Ag today will be March 11th. We have kind of transitioned this program to a bi-weekly program now, with things hopefully opening up a little bit through the COVID situation. So we will be doing this every other Thursday unless the need arises to have a timely presentation weekly. So our next one will be March 11th, and we will be discussing soil sample interpretations. You see the flyer there on your screen now. We're going to have representatives from Waypoint as well as the Virginia Tech Soil Testing Lab to talk a little bit about each of their processes and how to interpret each of the reports from those labs. So certainly that this is not something new to veteran producers, but if it's something that you think someone could be benefited from to help with that, please encourage them to join us on Thursday, March the 11th at 9 a.m. for Understanding Soil Test Reports. Finally, if you would, anybody that's with us, if you take a few seconds to fill out our survey evaluation for the program, you can find that in the chat window now. If you have a suggestion for a topic or something you think would be beneficial and timely, please let us know, and we'll be glad to try to put together some resources and speakers on the topic. So again, appreciate everyone's time joining us this morning, and hope everyone has a great rest of their week and enjoy some sunshine today.
Thank you.
Thank you, Dr. Easton. Appreciate you joining us.
I'll share this material with you right now.
All right. Thank you so much. We appreciate your time today.
Yeah, no problem.